you have any issues, let me know and see how we do it. Nice seeing you, everyone. After a week and a half, I had missed the class, so I'm really happy to be here. Happy to be back in here. Too bad that we have only 2 more weeks, and then we are gonna be presenting our final projects, and then on or 2 weeks including the final projects, and then we're gonna be ready on winter break. I'm pretty sure that everybody's looking forward to it now. Today we are going to have a quick. I have a few comments related to the project. Thank you for some of you that came to see me today during office hours with very specific questions related to your project. That's really it worked really well. I think that you have specific questions. We need to address those during the office hours. It's going to be easier. And for general comments like today, I'm going to bring on some of few comments only. There is a few teams that are already ahead of time and doing really well, and there's a couple of teams that are behind. I don't know if what was submitted might not be the whole thing. So just make sure that if you're behind, put the time on it and the plan. Some of you didn't submit a timeline or what was going to be done before the project, and some of you are trying to do everything between today and Wednesday. So just I do believe that can be done. However, it's going to be challenging because this is not the only class. So just make sure that you allot the time accordingly. And also, I was very happy to see the progress of some of you and to see some of the comic strips. They're really good. I enjoy the ones that I saw. So I'm looking forward to see the presentations and that you can share that with your classmates. Is there any general question that any of you may have? No? Okay, hold on, someone is coming in. Okay, so no questions. Perfect.
A question.
Yes.
About the presentation. So how long does it have to be?
Oh, the presentations is gonna be total 10 minutes, the presentation, and then 5 minutes Q&A. Okay? Any other? No? Alrighty, so as you can see, we're gonna try to finish our pollution problems today. We have 3 or 4 more. And then we are going to go into solid waste. We are going to start the topic. It's a very simple one. We'll see how far we can go, and that's going to be the last topic of the class. We are not going to be able to cover the last one, the water quality one. And so don't worry about the water quality.
Wait, so is there any more topics after air pollution?
Yes, solid waste.
Oh, okay.
Yes, so you can see on the agenda, right?
Professor, one question.
Yes.
For air pollution, we still have to submit the class notes except the video, right? The notes from the video?
Oh, yes.
Okay.
And actually, if you didn't submit, some of you submitted the notes and some of the videos. So what we can do here is just use that as a submission of the notes again. But I'll if you already submitted, so what you need to do is maybe finish the project, these problems today, and just add that to it. All right. That will be the submission for Saturday. I believe that we have to finish this week. I'm hoping that today, but if we can't finish today, we're gonna be finishing by this week. All right. So if you already submitted the notes from the video, what you just need to do is add up everything, including the project that we're gonna do today, and then start looking at your practice problems. The reading notes. Some of you were coming today and asking about them. I'm glad that some of you have started. It's a very lengthy chapter, and you're going to be responsible for all the theory and the formulas. Okay, so this is a very intense one, and you need to make sure that it's comprehensive, and you know how to use those equations. So it's several parts in there. Okay. Regarding the exam, some of you were asking me if I was going to talk about it on class. No, because everybody has different problems. It's going to be really difficult to address in class time. So what we're going to do is, if you have questions, as you have done, some of you came today to my office hour, please come to office hour and I can answer any questions. So one of the questions that came up during the office hours today was, my grade includes the extra credit? Yes. Those students that got extra credit, the extra credit is included already on your grade. If you notice, if you look at the average was really high, and it was because the highest grade was above 100, because the student, a couple of students did really well, and they got extra credit too, so it's above 100. So that's why it's not out of 100. Is the highest number is more than 100. So the extra credit was included. Okay. So since we are ready to start talking about air pollution, let me escape from this presentation, and I want to share my iPad now. Okay, so we're gonna go to problem number, we need to do problem number 5. Is that correct?
Yes.
Yes.
Okay. Let's look at the statement. We have a stack that is emitting 80 grams per second of NO and has an effective stack height of 100 meters. The wind speed is 4 meters per second at 10 meters, and it is a clear summer day with the sun nearly overhead. Estimate the ground level of the NO concentration. Add 3 different things. Directly downwind at a distance of 2 kilometers. Is that the right problem, by the way? No,
I think that's problem 4, and
Yeah, I'm
also
so
we can't
sorry.
see your screen.
Oh, you don't see my screen? Oh,
Or we just see, like we see PowerPoint.
really? Okay, hold on. So what's going on here? So stop share. Okay. Alrighty,
Can you give us the answer to number 4, by chance?
Okay.
4B and 4C?
Okay, someone can have the answer. Well, let's see if you, Matthew, go what you got, and I'll go and look my answer too.
For B, I got 227 micrograms per cubic meter.
Anyone?
I got the same.
I got 212 micrograms.
Yeah, I got
per
212 too.
Meters
Well,
cubed.
yeah, we had to get it from a graph, so it could be a little different.
Is 242 out of the range? So that's what I got.
It's close.
I think it all depends, like Matt said, based on what value we pick from the graph. Our answer is going to be a little different.
But the number should be very close. Even if you pick a value slightly different, they're usually very close. Hold on, I'm okay. Now you can see my screen, right?
Yeah.
Yes.
Yes, now we can.
On problem 5, right?
Yes, problem 5. All right, I'm not going to start. So the question was the answer for B? Or for
Yeah, 4B.
For B, I got 212 micrograms per cubic meter at 0.7 kilometers. That's the maximum concentration. Okay? And then for C, what did you get?
57.1 micrograms per cubic meter.
Okay, that's what I have. And the X is 2 kilometers and Y 0.1 kilometers. Yes?
Okay. Perfect.
Okay.
Well, that was given, right?
Yeah, that was given. That was given, but I think that it's very important at the end to specify the coordinate of the location of the concentration. Alrighty, so we're gonna read the problem, and just to make sure that we have some practice, we're gonna do this a little bit different. We're gonna read the problem. We want to understand. You're gonna start solving it. Okay, I'm gonna give you 10 minutes to work it out, and then we're gonna come back and look at the final answer. So the problem says that the world's tallest stack is on a copper smelter in Ontario, and it stands at 380 meters high and has an inner diameter at the top of 15, and at the top is 15.2 meters. The gases are released at 130 Celsius. That is the emission temperature. And the velocity is 20 meters per second. The ambient temperature is 10 Celsius, and the winds at the stack height are 8 meters per second. So that 8 meters per second is the wind velocity. We need to use the Briggs model to estimate the effective stack height. What was the letter that was used for the effective stack height?
Isn't that capital H?
Capital H, alrighty. And if we know the height of the stack plus the delta H, we can calculate the effective stack height, correct?
Yes.
Okay, so let's do this. Do a drawing of the stack and the problem, and go and find what is the question that we need. We need to assume that it's a slightly unstable atmosphere class C. We have two different equations to calculate delta H. I want you to go and look at your notes, determine what is the delta H that we need to use. In this case, we have unstable, we have two different situations. Which are those? Stable, unstable, right? So find that equation. Does everybody know where I'm going here?
Yes, talking about the plume rise, correct?
Yes. If you haven't watched the video, then you don't know what I'm doing. But I'm assuming that everybody has watched the video. All right? So I'm gonna give you 5 minutes to get the drawing to find the questions, and then I'm gonna be checking how it looks like. Be ready to share your drawing. If you can do it electronically, you cannot do it electronically. It's then probably you cannot share. But so let's make the drawing, do the situation with the stack, and the wind, and the temperatures, and select your equations.
Lester, are you still there? Here.
How's it going?
Oh, I can hear you now. I couldn't hear anything for a little bit.
Oh, no, I'm here.
Oh, okay.
So how's it going? Someone has a visual?
Should you just be solving for F and C for that equation, for F and S for that equation?
For that equation, what is the equation? Okay, so we're talking about the equation. So let's identify the equation.
Well, wouldn't it be because it's unstable? It'd be delta H equals 1.6 F to the raised to the 1/3 times XF raised to the 2/3 over UH.
Is everybody okay with that conclusion? Yes or no?
Yeah.
Okay, so this is
Okay.
very important. You're gonna need it on the final. You need to determine unstable or stable conditions and what is the question that you need. So yeah, that's correct. So we have determined that we need to have or use this equation. Now, remember, we said that the capital H, effective stack height, is gonna be H plus delta H. Do we know H?
Yes.
Okay, and we now can determine this one with the equation, the delta H. What else? What else do we need to determine? And I think that Matthew was asking already, do we need to just calculate the
F.
F?
We have to determine the F.
Buoyancy
We need
parameter.
to-
I was looking at the wrong equation, so I added S. But yeah, we need the F factor.
Okay, so we need to determine
Buoyancy. That's
buoyancy, and we need to determine XF, right? And do we know UH?
is 8 meters per second.
Is 8 meters per second. So we know UH. Perfect. So my equation for F, I'm sorry, hope this is right, is going to be equals to G R square, the velocity of on the top, and then this is times 1 minus the temperature and the ambient, or the divided by the temperature where we are releasing the emission. Is that correct?
Yes.
Okay. And we know that, let's start here now. Hey, hold on, how does the situation looks like? So everybody knows where we're going? Do you have a visual before we move into the solution? Can someone share?
You want an answer for F?
Yes. Yeah, hold on. Can someone share the visual of the?
Oh, no, I didn't have a picture.
No, nobody has a picture. You know that picture is worth $1,000 $1,000.
Draw a really ugly one on Paint right now.
Okay, can you share it? In your exam, you need to do a picture, and it's gonna be some points associated to it. That's what I'm trying to make sure that you do a picture to show me how it looks like, because many of you didn't do very good pictures that represented accurately the problems in risk, in the mass balance part in the exam. So someone can share. Just feel free to share. Everybody can share right now. Just let me know if you're sharing. Anderson, can you share?
Yes, and I'm drawing it out.
So it's a
So,
very simple one, nothing fancy.
like something like that, where you have your UH here.
Okay, are you sharing? No.
Yes.
Okay, I need to stop sharing. Sorry. Hold on. All right, there you go.
Very ugly. Here's ground.
Okay, perfect. And the diameter, where do we find the diameter?
It's given.
It's given, but because you have a wider on the bottom and narrow on the top.
So wait. Oh, am I supposed to just assume it's like one whole plume like that?
Oh,
Like
no,
a rectangular plume?
no, it's fine. But the diameter given is, where do we find the diameter given? Everyone.
It's in the problem statement.
It's in the problem statement, but it's at the very top. It's where the gas is being released. Right? Okay, so it's on the top. And the wind velocity is going to be that VH in there, right? And then the velocity where the gas is released. Alrighty. Perfect. So this is important. Many of you were not able to successfully draw the situation, and I want to know you understand by looking at your drawing. That's what I'm taking time on this. Okay. Thank you so much, Anderson.
Professor,
Yes.
in this problem, do we know the plume's behavior? Like, is it lofting or is it looping? Or is that something that we don't have to really worry about?
If you look at the different conditions, you might be able to tell what's happening after is this dispersed. But at this moment, you just know the conditions right outside of it. What you will need to do is use one of the models to look at the distribution downstream, all right, downwind. You need to do a little bit more of work to be able to determine how it is behaving.
Okay.
Calculating the concentration downstream. Alrighty. Thank you so much, Anderson. It looks really good, really well. That will be something that I will be expecting in the final. That's why we're taking time to do this. Okay, so let me go and share now my screen. Seems that some of you already have the calculation for F. Since we know everything in here, what is the answer for F now? Some of you have it already, Matthew? Who has it? Someone on the chat was telling me 3,370.
Yeah, I'll second that.
All right.
Centimeter there in Kelvin.
Okay. The temperature is going to be in Kelvin since F is larger than 55, right? This is larger than 55. What happens with calculation of XF?
XF is going to be equal to 120 multiplied by F raised to the 0.4.
Alrighty, so can you do the calculation of XF and tell me the number?
3,092 meters.
3,092 meters. Okay. Is everybody okay with this number? Yes.
Well, how do you get it though? I'm not really sure.
Oh,
Or just use the question.
Wait, why isn't that last point in the parentheses to the 1/3 power?
To the 1/3, what do you mean?
So the stuff that's parentheses, like in the equation that was given on your PowerPoint, it's the power of 1/3. So
This one?
0.50. Yes.
The temperature?
Yeah. So
That's when calculating delta H.
no. Oh, that's under stable conditions, right?
This
Yeah,
is
that's under stable conditions.
this is F, and we have stable conditions. All right.
Okay, so F changes depending on if it's stable or unstable.
F
Or-
changes Fx.
Just F in general, because here I'll just
No, F doesn't changes. What changes is delta H.
So I'm curious why we don't have this 1/3 variable in this equation.
Because for the F equation,
We're gonna.
it's not raised to the 1/3.
It's not raised to 1/3.
No.
Oh,
No, it's not.
oh, so that's just there because.
All right.
Okay, got it. Thank you.
All right. So now we have XF. Can we calculate delta H? We know everything now?
Professor,
Yes.
in the PowerPoint, under the equations, the F equation does say it's to the 1/3. So is that incorrect on the PowerPoint?
Let me see. Who has a textbook handy?
It is because on the textbook on page 463, you'll find that there's no 1/3 power.
It's not to the 1/3, right?
Okay, thank you.
Okay, thank you. I'll fix that. Thank you so much for catching that up. Alrighty, so not to the 1/3. This is correct. What do you have for delta H?
$635 for the plume rise.
Alrighty, 635 meters. Can someone check the number? Chat confirms that is the same.
I got 636.
Oh, it's about the same thing.
Okay.
Oh, what happened here? I'm sorry, I apologize. Okay. Yeah, it's sometimes when we're rounding up that happens. All right. And now finally we can now calculate the effective stack height. That we said that the height was 380 meters, and we just calculated that the plumb rise was going to be 635. The total is 1,015.
Yeah.
All right. And this is the effective stack height. Okay, so now what the question that was asked earlier. So how do I know what kind of behavior is going to exhibit this distribution under these conditions? What you need to do is model the concentration with distance or with time. And that will tell you how it's going to be distributed. Now you notice that the vertical distribution here is significant because the plumb rise is way larger than the stack height. Do you notice that?
Yes.
Which coincides with the unstable conditions. So at this moment, you cannot really tell what kind of situation you're going to have, but then you can do a little bit more work and model how is it going to behave under these conditions. Okay. So any question about this one? No? Alrighty. I didn't include the details of the calculations because you have seen those equations already. And it's straightforward. Yes.
So to get like the 3,470 meters to the fourth divided by seconds cubed. So do you get that from like inserting certain values into the equation? So I'm wondering where do you find those values?
Yes, all of them are given.
Oh wait. Oh, okay, I see. They are given. So the G
Yes.
is the gravity constant, right?
Yes.
G?
Mm-hmm.
Okay. I see.
Yes.
Well, I probably just have to look at it in the book, maybe too, as well.
Yes, and it was part of the video that we were watching, so just look at your notes.
Or I guess I'll just have to go back and look at that too.
Yes.
Yeah. Okay.
Alrighty. So remember, everyone, if you haven't done it, pull out your notes from the video because we are going to use all the questions that I talk about there. All right. So problem number 6 is a problem that I talked to you about that was going to be very useful if you buy a house because it's going to be helping you to look at the concentration at a house that is a distance from the freeway. So let's read this problem. So a freeway has 10,000 vehicles per hour passing a house that is 200 meters away. So it's fairly close, too close, I think. Each car emits an average of 1.5 grams per mile of NOx and winds are blowing at 2 meters per second across the freeway and towards the house. Estimate the NOx concentration at the house on a clear summer day near noon. Assuming that NOx is chemically stable. So this assumption is going to be very important. And it's not true, it's not accurate, because in reality, NOx is not stable, it's going to be reactive. But we're just going to assume to make our problem a little bit easier. Okay, so let's draw this. I've been telling you, we're going to start with a drawing. So in the previous problem was your turn, now it's going to be my turn, and we're going to be taking turns. So we have our freeway, very simple, right? Very simple freeway. And then 200 meters away, just assuming it's a perpendicular distance, we're going to have a little house where we're going to be looking at the concentration of NOx on a clear summer day near noon. And usually I have Pepito living in here. So this is Pepito, and Pepito is a little kid and we're concerned about his health. So let's see what is the concentration of NOx's in a summer day. Or you can think of, should I buy this summer house located 200 meters from the freeway because it's super cheap and I can afford it? Well, we'll see. We'll see if it's a good investment. So what's happening here? We have, it says that each car is going to be releasing 1.5 grams per mile of NOx. Where would you get that information from? Some of you are working with transportation right now, right, for your project. What do you think that you can, is that something that should be easy to find somewhere?
Shouldn't be provided by the manufacturers?
Exactly. So there has to be some information provided by the manufacturer based on the efficiency and the emissions of each car. It's going to be different. You can also have an average depending on the type of vehicle, right? So we're going to say that it's an average, like it says in here. For any type of vehicle, some of them might be better. The hybrids might be less, and the other cars might be higher than this value. Alrighty, so we have that, and then it says per car, so we need to include the per car in here. What is the velocity of the wind? 2 meters per second. So we have wind that is blowing towards the house, right? And we're gonna have the emissions coming from the cars that are on the freeway, and they're gonna be dragging that into Pepito's house, okay? I know it's cute. Someone is saying that Pepito is cute. Anyways, let's see. Pepito cute is safe. We have 10,000 vehicles. That is the number of vehicles that we are gonna have per hour. What else do we know? The distance. This is 200 meters away, and this is our X. Do you remember any equation on the video to model pollution emitted on a line?
The line source dispersion model?
The line source dispersion model. Thank you so much. So the equation for the line source dispersion model was Cx is equals to 2Q, yes?
Yes.
Divided by 2 pi, and this is to the square root. Sigma C times U. Can you check my equation, making sure I don't make mistakes?
It's right.
Okay. So this is the equation that we're going to be using in here. To the term, do we know the velocity of the wind?
Mhm.
Yes. Do we know Q? In the PowerPoint or the video said that Q has to be in what units?
Grams per meter.
grams per meter second. All right. So do we have anything that is in grams per meter second? Not really, right? So we need to determine Q. What about sigma C? How do we determine sigma C?
From the table?
Is that from
So
like the stability?
Yes, from the tables, right? Remember the sigma C and the sigma Y? In this case, it's in a line, so we don't need any sigma Y. We're just going to be looking at sigma C, so it's a table. So we already know how to do that. So we know how to do it. And then once we determine Q, and then we can get sigma C, we can determine the concentration at 200 meters, correct? Where Pepito lives. So this is what we're going to be doing now. Let's look at the statement here. Go to table 7.7 and tell me what classification do we have in here, A, B, C. What class is this? Let's look at
It's
class.
AB.
Is AB? What does that mean? How is this going to be helpful now? Well, we need to determine sigma C, right? Sigma C, and we need two parameters. We need the X and
You
X.
be more conservative and make it stronger.
Okay, so the proposal right now is making more conservative, making stronger. Is there any other proposal? No? Well, I have a different proposal just for the sake of, I know that some of you are like, oh, no, the smallest value, the largest value, you like the extremes. We can find sigma Z for class A and sigma C for class B, and then average them, which at the end of the day is kind of the same of what, I think it was Matthew proposing that. All right. So use table 7.9. And give me the values for sigma C class A and sigma C class B. And you know that it's at 200 meters.
It's 29 for A and 20 for B.
29 meters for A and 20 meters for B. Is everybody okay with me?
Where do we come up with the A and B again? That's the only part I'm wondering about.
Oh, you need to go to table 7.7. Table 7.7 as in the video, shown in the video. In the video, it take a lot of time to go and explain that. And then based on that, you can check if it is ABC, etc. Right, and then the sigma C. So is everybody else okay with that? This is what you're gonna be doing on the exam. You need to know how to use those tables. If you haven't watched the video, then we're not ready for the class today. And if you want to make the notes, please make the notes just to make sure, because I know that we're just practicing right now. So it can be like a little bit blurry still. But make sure that you put the notes in there, where table or what figure is.
Never mind, I see now. Just
You
needed
got it?
Yeah, I just
Okay,
needed
yes.
I just needed a refresher. It's not quite fresh in my mind. I need a refresh my
I
mind.
know, I know, but that's why I'm going a little bit slowly today, because I want to make sure that you guys go and look for the table. All right?
I understand now why.
There's in the final, I am not going to take you on the table. So you need to know how to go. All right. So we have, what sigma are we going to use now? 26?
4.5.
What do you say, 4.5?
was 24 and a half, right?
Okay, 24 and a half. Everybody okay with this?
Yes.
Alrighty, 24 and a half. Let's do it. This is the average. Okay, good. Now, what if someone picks 29 and someone picks 20? Technically, it's okay. But kind of to represent both, it's kind of the average is better. Alrighty, how do we calculate Q? That's the hardest part in here. We want a concentration in grams meter second. So what do we know? We know that we have 10,000 vehicles per hour. We know that each of the vehicles is going to be emitting 1.5 grams of NOx per mile per car or vehicle. Let's just put vehicle in here because we have vehicles. And if we do that, vehicles cancel each other, and then we have grams per hour per mile. So we just need to do some conversions in here. Technically, with this, we already have the units that we're looking for, isn't it?
Mm-hmm. Yeah.
We just need to convert the hours into seconds, the feet, the miles into meters, and that's it. So to do the conversion, what I need to do is multiply 1 hour divided over 3,600 seconds. And then I know that in 1 mile, we have, is that 5,280 feet? Check my number, please. And then 1 foot, we should have 0.305 meters. Check my conversion factors if you disagree. As long as everybody's okay, I can change the number. Let me cancel units, hours with hours, cars already canceled, mile with mile, feet and feet. And then we end up with grams of NOx per second meter. Okay. So everybody okay with these numbers?
Yeah, the conversions work.
All right. Who has the answer?
1.15 times 10 to the negative 3.
Okay, yes or no? Someone on the chat says no. What do you have on the chat?
I got 0.0026.
So if it is scientific notation, it's
I got the same as Sam.
2 point.
I think it's
Yeah.
2.6 times 10 to the negative 3.
All right. So,
That's what I got.
all right, that sounds correct. So it's grams meter second. All right. So this is my Q. Now I can go and put all the information on the question, right? And to determine the concentration at which Pepito is going to be exposed during summertime. All right. Okay, Pepito, hang in there. We're gonna come and rescue you from contamination. Okay, so we have 2 times 2.6 times 10 to the minus 3 grams meters second divided by 2 pi and the square root of this times, what is the velocity? 2 meters per second. And we said 24.5 meters for sigma z. What is the concentration?
42 micrograms per cubic meter.
42. Oh, you converted the grams to micrograms?
Yeah, my
Micro.
calculator did for me.
Alrighty. Per cubic meter, okay. Is everybody okay with this number?
I got the same.
Yep, same thing.
And actually, I cancel in here and it's not canceling. So hold on, let me just. I'm just gonna erase. I should not have canceled this. Let me just fix the units in here. This is 2 meters per second and 24 meters there. Okay. So we all in agreement, 42 micrograms per cubic meter. How do I know if this is good for Pepito or not? What would you do? Engineers.
Look at another table.
Yeah.
What table?
Risk assessment.
Risk assessment? No. What table? Yeah, there's a table, but not risk assessment. It's in air pollution table. Do you remember the standards? Okay, go look at the standards. We have 1 hour.
7.10.
So per standards, what was the value?
Well, it was table 710, and the standard for we're doing nitrogen dioxide.
Yes, NOx.
Or
So what do you find in that table? NO2?
100 micrograms per cubic meter
100?
annual. Yeah.
And this is 1 hour or 8 hour?
That's annual.
Annual, just annual?
Yeah.
All right, it doesn't give you the time.
It's annually.
Okay, so what do you think? Is Pepito in danger or it's okay according to the standards?
Should be acceptable according to the standards.
So according to the standards, it is acceptable. It should be okay. But let me just go back and double check in here. I remember we have a table.
Can we use this table 7.3? Is that table not good?
Well, the table point 7.3 is good for the air quality index. But let me look at 7.1 first. We so NOx is any nitrogen compound that has a different number of oxygens. In this case, we just have NO2, and we have the annual mean. All right, that's the one that you gave me 100.
But this is in parts per million, though. That's in micrograms.
Oh, I see. Okay, so we were looking at different table. All right, so you know how to do the conversion from milligrams per cubic meter to parts per million? Yes, you know it, right? Okay, we're not gonna do it right now. I want you to go and do it as a homework. So let me go here. So at home, take this into ppm and compare to NO2 table 7.2 standard. Okay, so when you submit your notes on Saturday, make sure that this problem is extended such as that you can compare that value directly with the standard and say if Pepito is good for the summer under these conditions. Okay? Where would you find the equation to the conversion if you don't remember?
Chapter 1?
Yes, chapter 1, the chemistry notes, right? We provide an equation to convert that ppm into grams or milligrams per cubic meter. So yeah, use that one. So that was I was telling you, we put a lot of time on chemistry, but chemistry is coming back to all the different topics. Okay. So we finish this problem. Just go and do the conversion. Technically, if this is stretching here that I'm circling here, this is a practical application. Why do I need to do all this? Because of this, you need to be able to tell or look at the concentrations at different times, at different locations, the maximum, the minimum, and then compare that to the standards and see the public is safe or their health can be compromised due to it. So that is why we need to do all these calculations. That is the bottom line. If you were to buy a house in there, you will do some exercise like this to determine if you really want to be there in summertime when you're supposed to be on vacation under these conditions. And if the standards are met, probably you will need to have some sort of ventilation to ensure that you don't inhale the contaminant. All right. Any questions about this one?
Wait, so what do you do with table 7.1 again?
With 7.1, you find the standard for NO2. But the standard is in ppm.
Okay.
So what you need to do is put them on the same units. This is micrograms per cubic meter, and this is ppm. Just convert them. Make sure that you can compare them.
Okay.
Okay. Right, let's move on. Problem number 7. We need to consider a box model for an airshed over a city, and the city is 1 times 10 to the 5 meters on one side with a mixing depth of 1200 meters. The wind with no SO2 blows at a 4 meters per second against one of the sides of the box. SO2 is emitted in the box at a rate of 20 kilograms per second. If SO2 is considered to be conservative, estimate the steady state concentration in the air shed. This problem looks very similar to one of the ones that we solved earlier in chemistry and mass balance too. So again, this is coming back in here, and let's first draw the city or the model. It's very common to model cities as boxes. I hope that now it's a little bit it's better, clear for you. Why is because it's going to be really hard to have a irregular shape of a city. So we're just going to be assuming that it's a box, right? And we're going to be enclosing the box. Maybe you as engineer need to determine what are going to be the dimensions based on the extent. Maybe towards the skirts of the city is very rural. Maybe you don't include that part just to represent the urban area, or maybe you just want to represent the rural. Depends on the situation. So depends on the situation, you're going to be looking into how to model this and how far to go. So it's telling us that we have 1,200 meters mixing depth, right? So beyond that, probably the pollution might not be, if there is anything going up vertically, it might be minimal, or maybe the conditions are just keeping in here the contaminant in that area. And now you understand why the temperature could be keeping a contaminant at a given depth. And that's why you can come confident with the 1,200 meters estimate. And then it says that we have one of the sides is 1 times 10 to the 5 meters. So I'm going to go by the side where the wind is coming or facing the wind. So being that said, that means that the wind is coming on the left with a velocity of 4 meters per second. And do we know the concentration of SO2 coming into the city with the wind?
It should be 0, right?
Yes, it's 0. Alrighty. So where is the SO2 release then?
From inside the city, buildings, cars?
There you go, inside of the city. So I'm going to be putting the city in there. And we know that SO2 is going to be released. And we know that it is at a rate of 20 kilograms of SO2 per second. And that's released inside of the city. Now, SO2 is considered to be conservative. What does that mean?
There's no generation.
No generation. Okay. Good piece of information. Conservative, no generation. So K is equals to?
0.
Okay, 0. That's why we eliminate the term. And then steady state concentration. As always, we're going to be doing steady state concentration. All right. So let's, if we do this with mass balance, which is my favorite way to solve these problems, accumulation is equals to in minus out plus or minus generation. We already know that accumulation is equals to 0 because it's a steady state based on the information of no K generation, which is, if we were to assume that it's a first order reaction with concentration volume K, right? So that goes to 0, and we end up just with two terms, in minus out. All right, so in equals out. That is going to be the guiding equation. What's going in?
The SO2 being emitted from the buildings inside houses.
Alrighty, the SO2 that is being emitted. What are the units for SO2? Are those concentration units? Are those flow rate units?
No, those are the generation units. So it's gonna be concentration times the Q, right?
Yeah, so it's the mass rate units, right? Is what we need the term to be in. So it's gonna be 20 kilograms per second, and this is the SO2. All right. So these are the units that we need, mass rate units, the mass per time. Okay. Is there anything else going inside into the box?
The vent.
The wind. All right. So now remember, what units do we need to have in the next in term? At the end, we need to have mass over time. So we have the wind. We know the velocity is 4 meters per second. What else do we know? What is the concentration? Well, hold on. Before concentration, this is the velocity, but in reality, my equation says Q times C. How do I get Q? Theoretically, what is the formula to calculate Q? Velocity times?
Area.
Area. What area?
Cross-sectional area.
Cross-section area perpendicular to the flow. So is this green area, right, through which the flow of the wind is perpendicular? Do we know the area?
Yeah.
Yes. 1 times 10 to the 5 meters times 1200 meters, right? So this is my area, and the concentration is? How much SO2 is coming in?
0.
0, so oof. So why do you make me do all this? Because I want to make sure that if the concentration is different from 0, you know how to do it, all right? And then minus what's going out. What's going out?
The wind speed times the area of the cross section.
Okay, so the wind speed, conservation, the fluid, Q in equals to Q out. And then what concentration, Anderson?
The concentration of what's inside the box model.
Exactly, the concentration of what is inside. So we're going to have now on our equation the velocity, or the Q, 4 meters per second times that area there, the cross-section area that we already discussed about, times the concentration out, which is the one that I'm looking for. And all of this is going to be equals to 0 because we're under steady state. So can we solve the equation for C out? You need to well, this is gonna be equals to 0, so it's gonna be 20 divided by this term in here. We might need to do some conversions in there. We need to do conversions. Well, kilograms might be a very tiny number if you have kilograms. So maybe you see if you can convert to grams or milligrams. So what is the concentration that you get? Okay, we have 42 times 10 to the minus 9. That's kilograms. I'm assuming kilograms per cubic meter. Can someone verify this number?
I got the same thing.
Alrighty, and if we put in micrograms, we get the same number just in micrograms, isn't it? Okay, and why is that? Because in a gram we have 1 times 10 to the 9 micrograms, all right? This was chapter 1, 2. So we need to be very now comfortable with these conversions. Okay, so again, this is a problem very similar to the ones that we have solved. I prefer mass balance approach. There are different ways of doing these problems. The next problem, which is the last problem, is related with indoor pollution. It could be done via mass balance too. However, I'm going to show you how to use the equation that was given it's given on the textbook. All right, questions about this one before we move to the last problem? No? Okay, so everybody's okay. The chat says okay. Thank you so much. The last problem of air pollution. It's amazing. We haven't ever done that many problems in class. Alrighty. We have a single-story home with infiltration rate of 0.5 ACH. What is the meaning of ACH? ACH? I can tell you that at least 10 of you could be coming and asking me to tell you what ACH on the exam is, and you need to know what ACH is. Air changes per hour. Okay, so it's the number of times that in an hour the air is filtrated. Okay, air changes per hour. And it has a 200 square meters of floor space and a total volume of 500 cubic meters. If a 0.6 picocurie meter square second of radon, so the the Curie units are for radioactive chemicals. Pico is a very small concentration. Picocurie, meter square per second of radon, is emitted from the soil and enters into the house. And a rate constant is 7.6 and 10 to the minus 2 per hour. What is the reaction order here? What is the order of this reaction?
Is it first?
First order.
Is first order. The units, right? 1 over time. Estimate the steady state indoor radon concentration. So that sounds mass balance. Yes, it could be done with mass balance. I'm not going to use the mass balance approach. I'm going to use the equation that is given on the textbook. But at the end of the day, you could use either approach and it should be giving you exactly the same answer. So this problem is very, very relevant to the pandemic, by the way. I don't know if you have ever thought about it, or maybe your family is already doing this, but a lot of you, I actually bought an air purifier for my house, and you need to know about the cubic or the volume of the rooms and the square area of the room, and it will tell you how often the whole volume of air inside is going to be filtrating. So it's applied to radioactivity, but it could be applied to air quality. In this case, for COVID, especially you have someone that has underlying conditions in your home, which is my situation, by the way. So I want to make sure that I protect my family member. So let's look at what we have. We have, how do we model this? It's a house. We can just say, to make sure that we can see this, it's like a box. We put it in here. And this is the house or the box, the room. And I know the volume of the house is, or the room is 500 cubic meters. And we know the area is going to be 200 meters in the space. And we know that the concentration, well, the filtration rate is going to be acting as like the flow rate. The flow rate or the filtration is going to be 0.5 ACH. What was the meaning of ACH?
Air changes per hour.
Air changes per hour. Thank you so much, Maria. Okay, and then we know that it's a K, 7.6 times 10 to the minus 3. So it's going to be reacting inside there. There's going to be a reaction, and it's going to be important for the changing concentration inside of the box. Radioactivity decays with time. Okay, so let's look at estimate the steady state concentration. All right, and what is the equation that we have? Do you remember an equation from the video? No? So the concentration, the infinite, right, or the steady state concentration inside is going to be equals to an equation that all the variables are defined on the PowerPoint. They were defined in the video and the PowerPoint that I gave you in class, or that you have on Blackboard. So this is the equation for the steady state concentration. And we're familiar with this C infinite. It looks like an infinite steady state concentration. Okay. Does it give you any information about where is the radon coming from? Look at the room. Look at the box in there. Where is the radon coming from?
From the soil.
From the soil, right? Only from the soil. So if we were to put the concentration coming in here after it was filtrated, the concentration of radon in here will be equals to 0. And in here in the room, it's a 0.6. 0.6 picocurie meter square per second. All right? So it's the amount per time per square area. That's what's happening. Okay. So our S is going to be the source emission. The V is going to be the volume. The CA is the ambient concentration, which we just look in your figure and there is nothing coming from the ambient, it's just coming from the soil. So this is going to be equals to 0. This part gets equals to 0. The K, we know the K. And the N is the infiltration rate. N is going to be the 0.5 ACH, or infiltration rate. So let's see. Do we know the source concentration? Where is the emission? It has to be, the source concentration has to be in mass per time. In this problem, we have 0.6 picocurie, which is our mass, divided by the area and the time. So we have the mass and we have the time, and we need to get rid of the square meter. What do I do to get rid of the square meter in there, or the meter square?
To multiply by the area.
Multiply by the area. Okay, so S is going to be equals to 0.6 picocurie meter square second times 200 meters square. And then what do you get?
120.
120 picocurie per second. Now we're ready to do the steady state concentration. Is going to be equals to 120 picocurie a second, and all of this is going to be divided by the volume. The volume is 500. Yes, 500 cubic meters, and all of this divided by 0.5 ACH plus the K value that was equals to 7.6 times 10 to the minus 3, 1 over hour. Okay, what do we get? Do we need to do conversions? Hold on. Yes, we need to do conversions because we have seconds in here and hours in here. So let's multiply this by 1 over 3,600 seconds. Does that make sense?
Yeah.
1 hour, so the hours cancel out, the seconds cancel out, and then we can get picocurie per cubic meter. And what did you get?
I got 0.48.
0.48. Can someone confirm the number?
I can second that.
Okay. 0.48 picocurie per cubic meter. I get a different number. But I made a lot of mistakes. I'm not perfect. So it's everybody okay with this number then?
I got 6.7 to the negative 5.
Oh, that's a third different number,
I got a large number.
which is
240.
240. Okay, I get 1700 picocurie per cubic meter.
Yeah, I got like 1700 something too.
1700. Okay, at least we have two numbers.
Yeah.
So it's 120 divided by 500,
Yes.
right?
So do you add 0.5 plus 7.6 times 10 to the negative third, and then you multiply it times 1 over
Yes.
100 seconds?
Yeah, this is added.
Yeah,
These
okay,
two
that's how I
are
that's
added.
how I did it.
And then times 1 over 3600. Okay.
I got the answer on the board now, but why do we divide by 500, the 120?
Oh, because of the formula. The formula says that your S divided by volume.
Yeah. Okay.
I'm just following the formula, right? Okay. I want to hear from someone else because we haven't agreed on the final number. Samuel, Alejandro,
I'm getting 0.48 as well.
0.48, all right. So that was Abraham. Lena, Antonio, what do you guys think? Jaime.
Got 1700 something.
Oh, wow. Okay, so let's do this. Let's go back and double check either 0.48 picocurie or 1700.
I got 1700 too. So kind of the same answer.
Yeah, I got that.
Okay, someone is making a mistake. This is the same mistake, maybe the way it's written. All right.
The order of operations is wrong for the 0.48, so I would change it to 1700 with that bracket there.
This? But what is the mistake?
That's without the red bracket at 0.48. So with the bracket there, it's 1702.
Yes, no, the bracket has to be there. Look at the question.
Yeah.
The question, these two are added, right? And I just multiply times the conversion in this case. So it has to be those two are added and all that are converted. All right.
So air changes per hour could just be inverse hours.
Oh, air changes per hour is AC per hour. Yes. That's why it has to be converted to seconds. Air changes per hour is the unit.
Yeah, I'm getting 1702 now.
Okay, so I'm really happy that you made that mistake because it allowed me to see where the confusion was in terms of the ACH. ACH is the air change. And it's time to go per hour. So I'm gonna end up in here. Air change per hour, so it has to be converted to and it's 1700. Alrighty, thank you so much for the input. It's time to go. I will see you on Wednesday, and we're done with air pollution.
Professor, see you Wednesday.
See you Wednesday. Take care, Samuel.
Question,
All right, you as well.
real quickly.
Yes.
So with our reading notes, we just gotta cover we just gotta cover the whole chapter, right? We can.
Yes.
Just fit as much. And it's basically the same rules and stuff as the risk assessment. Just follow the same rules.
Yes. Yes.
Basically, try to fit as much as we can. Okay.
Yes, as much as you can to ensure that you have information in there and the formulas on the back.
Okay. Just no diagrams, pictures. I know this chapter kind of requires us to looking at some diagrams. So we would have that. We don't have to
If you need the plots or the tables, I am gonna provide that to you. Do not waste your space putting them in there.
Okay. Figured.
Because that is what I would call part of the design. They need to be given or available, so I am responsible for those tables. You just need to know how to use them, which one to use and when.
Okay. All right.
Alrighty.
Anyway, okay. All right. This problem.